Have you ever thought about interstellar travel? It sounds romantic to journey to other worlds towards the stars, but actual reality might disappoint you. The current maximum speed of the Voyager 1 probe is 10.5 miles per second. Even at this speed, the journey to our closest star, Proxima Centauri, would take about 74,600 years. Now imagine that one day humanity creates spacecraft capable of traveling close to the speed of light. About 186,000 miles per second. Sounds impressive, or maybe just impossible. But even that wouldn't be enough, because even at that speed, if we wanted to leave the Milky Way galaxy, it would take around 100,000 years. And what if we wanted to go further and consider not just interstellar travel, but intergalactic travel as well? That's where an even more serious problem emerges, namely a gigantic cosmic anomaly that was discovered in 2013. While conducting research, a group of astrophysicists found that our galaxy is surrounded by a massive cosmic void, which, according to the laws of physics, shouldn't exist. This isn't just a region with a lower matter density, it's one of the largest known cosmic voids. Its diameter could reach 2 billion light-years. If it were filled with galaxies, it would fit more than 20,000 Milky Ways lined up from edge to edge. The scale of this anomalous region is truly staggering. Light would take 2 billion years to cross it. But perhaps the most shocking part of this discovery isn't the size of the void, it's our location. We're most likely located close to its center. Our galaxy seems to lie at the heart of a colossal funnel, and, as scientists note, this could seriously affect our understanding of the structure of the universe. But if we really do live in a special, isolated corner of space, an inevitable question arises: what lies beyond it? Could the space beyond this void be fundamentally different in density, in structure, or even in the laws of physics that govern it? Today, more and more scientists are wondering, what would happen if we could cross that boundary and see the universe as it reveals itself on the other side of the void? Local hole. This was one of the most mysterious cosmic anomalies discovered in recent decades, named the KBC Void. When astronomers Ryan Keenan, Amy Barger, and Lennox Cowie first proposed the hypothesis of its existence, it caused a true shock in the scientific world. This is not just a patch of thin space, it's a violation of the very order of the universe as we know it. But what exactly is this void, and why could its existence change our fundamental understanding of the universe? To get to the bottom of this, we need to look into the past. The distant past. Rewind to about 13.8 billion years ago, to the moment when it all began. The Big Bang. The universe began expanding, suddenly, rapidly, in all directions at once. At that moment, energy expands evenly, like ripples in water after you throw a pebble in. It's believed that matter was disturbed just as evenly. This is the basis for the so-called cosmological principle. The idea that, on a very large scale, the universe should look the same in all directions and in all places. After all, matter should have spread out uniformly. Because of this, we can apply the same physical laws to nearby stars and to objects at the edge of the observable universe. Because the way things work here should apply everywhere. At least, that's how it was supposed to be. But data from recent years increasingly show that matter in the universe is unevenly distributed. Different regions of space contain areas of higher and lower density, which means the idea of cosmic homogeneity is already in question. But the structure of the KBC void stands out even with this context in mind. It's not just a less dense region, but an anomalously vast area in which some of the laws of physics may be different. Research shows that the KBC void has an approximately spherical shape and may extend up to 1 billion light-years in radius. That's 4 times larger than the Laniakea supercluster, which contains about 100,000 galaxies, including our own. These vast dimensions account for roughly 2% of the entire observable universe, making the KBC void the largest known cosmic void. But calling it truly empty would be inaccurate, if only because we're in it. Indranil Barnik, a postdoctoral research fellow at the University of St Andrews who studies the KBC void, conducted calculations and found that the matter density in the form of stars and galaxies within the void is about 20% lower than outside it. At first glance, the difference may seem small, but within the framework of cosmic laws and the vast scale of this void, it's something extraordinary. For unknown reasons, the universe has formed a gigantic spherical region where stars and galaxies are far less frequent than beyond its boundaries. Paradoxically, it's this very anomaly that, according to scientists, might help answer one of the biggest mysteries of modern cosmology: why the universe is expanding faster than it should. After the Big Bang, the universe began expanding rapidly, and that process continues to this day. The speed at which this happens is called the Hubble constant. To measure it, scientists use 2 main methods. The first is based on observing relatively close cosmic objects, supernovae and galaxies. By measuring how quickly they're moving away from each other, astrophysicists get a value of 45 miles per second per megaparsec. In other words, every second, the distance between objects about 3 million light-years apart increases by 45 miles. The second method goes deeper. It relies on the study of the cosmic microwave background, the ancient radiation that arose shortly after the Big Bang and is still spreading throughout the universe. This light has been traveling to us for about 13.6 billion years, providing scientists with something like a snapshot of the young universe. Based on this data, scientists are working on reconstructing a model of what the early universe was like. From that, they calculate how fast it should be expanding today. And this is where things get strange. The results from this method give a completely different value, around 41 miles per second per megaparsec. That's lower than the results from the nearby galaxy method. This discrepancy has its own name, the Hubble tension. If we only look at data from the cosmic microwave background, the universe should be expanding more slowly than what we actually observe. But direct observations tell a different story. The galaxies around us are moving apart about 8% faster than the physics of the early universe would allow. Astronomers haven't yet agreed on exactly what causes this discrepancy, but more and more specialists believe the key might lie in our cosmic environment, in the KBC void itself, and the explanation might lie in gravity. We know that massive objects like stars can pull in less massive bodies, planets, asteroids, and comets. And it seems the same principle applies here. The denser regions beyond the void are pulling on the galaxies inside it. It's as if they're trying to drag them out of the void, adding extra acceleration on top of the universe's natural expansion. This gravitational imbalance could be exactly what's distorting our measurements. Brian Keating, a cosmologist and physics professor at the University of California, San Diego, considers the void hypothesis quite plausible. In his opinion, it really could explain why the universe is expanding faster than expected. But, as he himself admits, that there are plenty of questions remaining. One of the main ones is how far does this void's influence actually extend? If its effect is limited to just our part of the cosmos, then it only explains the discrepancy locally, which means the global problem is still unresolved. It would truly eliminate the Hubble tension. In addition, Keating points out that Barnik's theory depends on which void model is used. Different models produce different results. They predict different galaxy behaviors and different impacts on the overall flow of matter in the universe. In the end, this is still just an approximation, a simplified picture. The void might be far more complex than it appears. But before we can talk about the effects of the void, we first need to understand how large it really is. And the problem is, recent data suggests the KBC void may be much smaller than previously thought. One scientific research group analyzed the Cosmic Flows 4 catalog, the largest database of galaxy distance measurements, They used the Tully-Fisher relation, which estimates the distance by comparing a galaxy's brightness with its rotation speed. According to their calculations, the size of the void is about 230 million light-years. That's almost 10 times smaller than earlier estimates. Of course, this doesn't mean that the gravitational acceleration effect goes away, but it's no longer strong enough to fully explain the discrepancy in the universe's expansion rate. So the question remains open. The void most likely exists, scientists are nearly certain of that, but it remains unclear how big it is. It might occupy up to 2% of the observable universe, or it might be far more modest in size. What's more, the data from the DESI project between 2023 and 2024, which maps the nearby cosmos in ultra-high resolution, suggests that these kinds of voids aren't rare. It's possible that our local void isn't unique at all, but just one part of the broader cosmic landscape. But don't think that this makes the universe any less exciting. On the contrary, the KBC void is raising more and more questions among scientists. Astrophysicists are interested not only in its potential role in resolving the Hubble tension, but in a far more intriguing scenario. What if we weren't inside this void, but outside it? What might the cosmos look like then? What would change in our observations? And most importantly, how would our view of the universe itself be different? Of course, the boundaries of this void are at such colossal distances that for humanity, reaching them will likely remain forever unattainable. But let's imagine we had unlimited time and access to technology that allows near limitless movement through space, pushing the edge of physical laws. In that case, buckle up, it might get a little bumpy.